Hi, in this last part of the VCR and heat pump system, we are going to talk about the multi-stage compression VCR. The multi-stage compression VCR can be used to improve the efficiency of the simple VCR cycles. We already know that for the compression process, instead of using a single compression step, we can apply multi-stage compression with intercooling to obtain better compression efficiency. Okay, we already know that the compression work for multi-stage system will be lower than the compression work required for the single stage system. Okay, so in these VCR cycles, okay, is a little bit more complex than the cycle that we have seen before. You can see that we have two compressors here. We have the low pressure compressor and we also have a high pressure compressor. So it means that in this example we have two-stage compression. Okay. Now between both stages here, we must have some intercooling, and in this case we will use cold vapor to cool down the hot vapor. Number 2 here is hot vapor. Okay, we will have to use the cold vapor to cool down this hot vapor. Okay, and the cold vapor we can have it by flashing it through an expansion valve. Okay, and then we separate just the vapor out. The vapor that we obtain from the expansion valve would be cold vapor. Okay, so in this VCR cycle we will mix the cold vapor and hot vapor together. Okay, so we can bring the temperature of the hot vapor from the first stage compression down. Okay, so you can see 2 plus 3, that would be 9. Okay, 2 plus 3, it would be 0.9. This is the mixing point. Okay, and then you compress the mixed vapor here. Okay, in the second stage compression to the high pressure again. Okay, from 9 to 4. Okay, so you have two-stage compression. This is the first stage here, and this is the second stage here. And the intercooling can be achieved by mix the cold vapor that we obtain from the flash chamber with the hot vapor that we obtain from the first stage compression. Okay, so we have two-stage compression here. So how do we get the cold vapor? The cold vapor that we use to mix with the hot vapor must be at the same pressure. So it means that P3 here must be equal to P2. So it means that you have to flash the liquid from the condenser to an intermediate pressure, okay, to get some vapor out and use that vapor to cool down the hot vapor from the first stage compression. Okay, so it means that in your cycle you will operate in 3 different pressure level. Okay, you will operate with the high pressure here. You will flash it to an intermediate pressure here, and after that you will use the remaining liquid to flash it further to the low pressure here. Okay, so it means that you operate within 3 different pressure levels. Okay, so you can see that in this system you have to invest more in terms of the some extra equipment. For example, you have 2 compressors. Okay, you have 2 expansion valve here, the first valve and the second valve, and you must have also the flash chamber as well. in order to separate the vapor from the liquid. Use the vapor to cool down the hot vapor, and use the liquid to expand further, okay, and then use it to absorb heat in the evaporator. Okay, so the cycle of VCR with multi-stage compression and intercooling would be as shown on the TS diagram here on the right hand side. Now you can see that the benefit that we obtain from the multi-stage compression VCR would be very similar to what we obtain from the cascade VCR. Okay, if you compare the VCR, this kind of VCR with the simple VCR with the single stage, you find out that for simple VCR or single stage VCR, the cycle would be on the red dashed line here. Okay, you compress from number 1, okay, to the highest pressure. This is high pressure, this is low pressure. You compress from low pressure to the high pressure in a single step, and then you cool it down in the condenser by rejecting the heat to the atmosphere or to the surrounding, and then to number 5, then you flash it in a single flash valve, single expansion valve. Okay, flash it down from high pressure back to low pressure again, and then enter the evaporator, okay, to continue your cycle. So you can see that the benefit that we can get here will be in terms of the decrease in the work requirement, okay, decrease in compressor work, decrease in compressor work when compared to the simple VCR. Okay, this red dashed line is the simple. Okay, and the other benefit that you can get would be in terms of the increase in the refrigeration capacity. Okay, this is the increase in refrigeration capacity. Right, so you can see that we have quite the same benefit that we have in the cascade VCR. Okay, all right then. Now let's have a look at an example that I want to show you the calculation on the multi-stage compression refrigeration with intercooling. Here in this example, we are considering a two-stage compression refrigeration system. Okay, we have two-stage compression operating between the pressure limit of 0.8 and 0.14, which is the same values of the highest pressure and the lowest pressure that we have considered in the previous example in the cascade VCR. 0.8 megapascal and the lowest one here is 0.14 megapascal. Okay, and the working fluid is also the same, R134A. Okay, the refrigerant will leave the condenser as a saturated liquid and then is throttled to a flash chamber. So from number 5 it will be throttled to number 6. You can see that at point number 6 you have two-phase mixture. You have vapor and the liquid. The vapor part would be number 3. Vapor part would be used to cool down the hot vapor from the first stage compression. 3 will mix with 2 to get 9. Okay. Now for the liquid part, Okay, number 7, it will be flashed further from the intermediate pressure to the lowest pressure from 7 to 8, and then it will enter the evaporator. Okay, so you can see that in this cycle we operate at the same pressure level that we have seen in the previous example. This is 0.32 megapascal. This is an intermediate pressure. Okay, now what we want to know is that we assume that the refrigerant leaves the evaporator as a saturated vapor. So number 1 here is on the sat vapor line. Okay, both compressors are adiabatic. Okay, adiabatic, but in this case you can see that enthalpy at the inlet and outlet of compressor are already provided. Okay, I'm not sure whether this one is isentropic or not, but it's adiabatic, no heat transfer during the compression. Okay, we want to determine the fraction of the refrigerant that evaporate, as it is throttled to the flash chamber. So it means we want to determine X6, okay, the vapor fraction when the refrigerant is flashed to the flash chamber, number 6. We also want to determine the amount of heat removed from the refrigerated space. So that would be QL dot here. Okay, and the compressor work per unit mass of refrigerant flowing through condenser. Because in this example we don't have the mass flow rate, so Q that we want to determine must be QL. Okay, QL and W net in. Okay, QL and W net in. Alright, and lastly we want to determine the COP of this refrigerator. You can see in this example all enthalpy are already provided. Okay, you know H1, H2, okay, H3, 4, 5, 6, H6, H7 and H8 and also H9. You already know everything, the enthalpy value, so you can just use them to calculate the parameter that you want to know, okay, by doing the energy balance in some processes. Okay, now let's first determine the fraction of the refrigerant that evaporate. So it's the vapor fraction. Okay, the vapor fraction at point number 6. Okay, X6. So X6 can be determined from the equation that we are familiar with. Okay, X6 would be H6, which is the enthalpy of the mixture at that point, minus HF, enthalpy of the sat liquid at that condition, divided by HFG, or Hg minus Hf, okay, or latent heat at that condition. Okay, so in this case you already know HF. Okay, HF would be the enthalpy of the sat liquid. You can get it from the table, or you have that from the previous diagram. Okay, HFG as well, you already have that, Hg minus Hf, okay, at state 6 or at 0.32 megapascal. Okay, so you can determine X6 vapor fraction from the flash chamber would be 0.2049. Okay, so that's the first answer. Okay, we also want to determine the amount of heat removed from the refrigerated space, or QL. Okay, in this case we want to calculate per unit mass of refrigerant flowing through the condenser. Okay, the refrigerant flowing through the condenser, okay, QL. Okay, so QL QL equal to 1 minus X6 multiplied by H1 minus H8. Okay, so QL, you have the 8 to 1. This is number 1. This is 8, right? Okay. This is 6. Okay. And this is 7. Okay. So you can see that the flow rate of the refrigerant which flow through your evaporator is not the full fraction. Okay, you have the vapor with the amount of X6. The remaining liquid would be 1 minus X6. It's only 1 minus X6. So the flow rate of the refrigerant flowing through the evaporator would be 1 minus X6 as well. Okay, only 1 minus X6, right? 1 minus X6. So the heat removal in the refrigerator space per unit mass of the refrigerant flowing through the condenser, which is the total flow. So you have to multiply H1 minus HA with the fraction here, the fraction of the refrigerant flowing through the evaporator. Okay, so actually H1 minus HA would be kilojoule per kilogram through evaporator. Kilojoule per kilogram through evaporator. Okay, and 1 minus X6 is kilogram through evaporator divided by kilogram of total flow. Okay, kilogram of total flow. So when you multiply 1 minus X6 with H1 minus HA, you will get kilojoule per kilogram of total flow. Okay, so this is why the reason why you have to multiply 1 minus X6 fraction with H1 minus H8 here to get the required QL value. Okay, so that would be 146.3 kilojoule per kilogram. Okay, we also want to determine the compressor work per unit mass of the total flow as well. So compressor work would be WCOM number 1 plus WCOM number 2. Okay, from WCOM number 1, the flow rate is only 1 minus X6. Okay, so you have to multiply with the same reason as I have explained above here. You have to multiply 1 minus X6, which is the fraction of the flow through the first compressor, with H2 minus H1. And WCOM2, the flow rate through the second compressor is 1, because you already mixed X6 with 1 minus X6, so that becomes 1. So it would be 1 multiplied by H4 minus H9. Okay. Now at this point you already know X6, H2, H1. Okay. And you can determine H4 and H9. Okay, H4 and H9. Actually H4 and H9 are not provided by the problem. I just make a mistake. I just explained that it's already there, but you have to determine H4 and H9 from the balance of the mixing point. Okay, so you have to determine H9 first. H9 is the enthalpy from the mixing chamber. So you have the mixing chamber here, you have number 2, you mix it with number 3, and you get number 9. Okay, 2 mixed with 3 and you get 9 out. Okay, so number 2, you have the flow rate of 1 minus x6. Number 3, you have the flow rate of x6. And number 9, you have flow rate of 1. Okay, so you do the energy balance around the mixing point. You have E in equal to E out. E in, you have x6 H3 plus 1 minus x6 H2, and that would be 1 multiplied by H9. Okay, so you can calculate H9. That would be 255.1 kilojoule per kilogram here. All right. Now, from 9, it will enter the second stage compression. Okay, so from 9, it will enter second stage compression. This is number 9, and it will go out at number 4. Okay, so this compression here, we know that it's isentropic. Okay, it's isentropic. So S4 will be equal to S9. Okay, S4 equal to S9, and the pressure at number 4 is 0.8 megapascal. So you can determine the enthalpy at this point. Okay, because you know two pieces of information. You know pressure and you know entropy at point number 4. So you can determine H4 from the refrigerant R134A table. Okay, this is from the superheated table. Okay, and now you know every value. You know H4 and you know H9. You can substitute them into the equation that we have developed in the previous slide, and then you can calculate the required power input. Okay, W in would be 32.71 kilojoule per kilogram. Now you can calculate the COP of this refrigerator. It would be QL divided by W in. Okay, you can take QL divided by W in here because they are both on the same basis. Okay, based on kilogram of total refrigerant flow. So you can use this specific form. Okay, this work is also per kilogram of total refrigerant flow as well. Kilogram total. So you can use this form. Okay, and the result, you can see that the COP of this multi-stage compression VCR is around 4.47, which is very similar to the one that you obtain from the cascade VCR. If you can remember, in the previous part of the cascade VCR, you have COP around 4.46. In this case, for the multi-stage compression VCR, you got 4.47. So you can see that the efficiency of the kind of two VCR system are more or less the same, are pretty close, okay, to each other. Alright then, that's the end of these examples. Now, before we close the lecture of the VCR and heat pump, let's take a look at some special kind of the VCR system. Okay, in the refrigeration system, instead of flashing your refrigerant from the highest pressure value to the lowest pressure value in a single step, you can do a multiple expansion step. Okay, multiple expansion step like this one. You may expand it to an intermediate pressure. Okay, you may expand it from high to intermediate pressure and then use the refrigerant to absorb heat from one cold refrigerated space. In this case, it is used to absorb heat from the refrigerator room, okay, the refrigerated space here, okay. And after that, the refrigerant that came out of the refrigeration chamber here, it may not become fully vaporized, okay. It may not be the complete vapor or set vapor. You can then flash it down further and use the refrigerant to absorb heat at a lower temperature, for example in the freezer here, okay. So in this case, it means that you can just flash in a multiple step and then absorb heat at different temperature level, okay. For example, in the refrigerator, you may absorb heat at say 4 degrees Celsius, control temp in this area 4 degrees Celsius. In the freezer, you may absorb heat at say minus 10 degrees Celsius, for examples, okay. So you can have multiple chamber at different temperature levels, okay. So this is called the multi-purpose refrigeration system. Well, I guess you already have this kind of refrigerator in your house already, okay. You have the freezing chamber separately from the refrigerated chamber, okay. So in this case, you can see that the heat removal would be QLR, okay, this part plus QLF, okay. QL would be QLR plus QLF, okay. All right, okay. And QLR may be just m dot multiplied by H5 minus H4, okay. QLF may be just m dot multiplied by H1 minus H6, okay. So QL would be the combination of the heat removal from two different chambers, okay. All right then. Now I will close this lecture with the heat pump, okay. The heat pump, we already know that the objective of the heat pump is the warming service, not the cooling service. We want to make use of the heat rejection to the warm region, not the heat removal from the cold region, okay. So in the kind of cold climate country, they may install the heat pump instead, okay. And this heat pump can be used in both objectives. In the winter, we can use it to warm up our house. In the summer, we may use it to cool down our house, okay. So to make it function in both objectives, we have to make some adjustment, or the system would be a little bit more complex, like I'm going to explain it to you now. So in summertime, okay, the heat pump in summertime, it will work as air conditioning. Air conditioning system. Okay, air conditioning system. So this would, on your right hand side, it would be your house, okay. You want to cool down your house, okay. And on your left hand side, it would be your the outside region or the environment, outside environment, okay. So it means that in the summertime, you want to remove heat from your house to the outside environment, Okay, so it will work as a refrigeration system. Okay, so in this case, let me start from the evaporator. This is the evaporator. So the refrigerant, okay, which is at low pressure here, and low temperature here, low pressure and low temperature here. It will be used to absorb heat from our house. Okay, absorb heat from our house, and it will become the vapor. Okay, and the vapor here will flow through what we call a reversing valve. In this mode, in the air conditioning mode, it will flow through the reversing valve in this direction, and then it will enter the compressor. Okay, enter the compressor. The cold vapor would be compressed, and then it will become hot vapor. Hot vapor will flow through this reversing valve again, but in this part here. Okay, and then it will go outside to be condensed in the condenser outside your house. So it will be condensed to hot liquid. Hot vapor will be condensed to hot liquid, and then it will flow back into your house again. Now in this case, it will flow through an expansion valve. Okay, in this case we have two set of expansion valve. Okay, for any mode, in the air conditioning mode or in the heat pump mode, only one set of expansion valve will work. The other set will be closed, or it will be shut. Okay, so in this case, in this mode, it will flow through, okay, this bypass valve. Bypass valve is more or less like a check valve. Okay, a check valve. So it will allow only flow in this direction, from left to right direction. It will allow the flow in only in this direction. And similar to the expansion valve, if you put the liquid flow in the wrong direction, it will not flow through. So in this case, you can't have the liquid flow through this expansion valve. So your liquid will flow through this bypass valve, and then it will flow through this expansion valve. Okay, you don't have the flow through this check valve of the second set here as well. So it will flow through the expansion valve, and then it will enter the evaporator again. Okay, like this one. So this is how the system works. Okay, in the summertime, it will behave as an air conditioning system. Alright, now when you are in the winter time, okay, we have to switch the operating mode from air conditioning system to the heat pump system. So it would be this picture. Okay, so on your right hand side is still your house. Okay, it's still your house, and on your left hand side is still the outside environment. It's outside environment. So in this case, you can see that we want to absorb the heat from outside and put it into the house to warm up your house. Okay, so the function of the heat exchanger will be switched now. Previously, you can see that the exchanger in your house is evaporator. Now it will become condenser. And on the other hand, the exchanger which is outside your house, it will become evaporator instead. Okay, now in this case here, I will start from the evaporator again. The refrigerant will flow through evaporator. Okay, flow through evaporator. Refrigerant will be turned into the cold vapor. Okay, it will absorb the heat from the outside environment, okay, and then it will flow through the compressor. So it will flow through the reversing valve here. In this case, you can see that it has been switched, okay, to the other side to allow the refrigerant to flow in the opposite direction. So you can see that the refrigerant flow into the compressor, okay, and the compressor will compress the cold vapor into the hot vapor, okay, and the hot vapor will flow through the reversing valve again, and then it will flow through the condenser here. Now the hot vapor will be condensed in the condenser and then rejecting heat into our house to make our house warmer, okay. The refrigerant will become hot liquid, okay. Hot liquid here will flow back to the evaporator, and it has to flow past the expansion valve first. Now in this case, you can see that the hot liquid here, it cannot flow through the expansion valve of the second set. Instead, it will flow through the bypass valve of the second set, and it will flow through the expansion valve of the first set here, okay. Check valve here will be shut, okay, will be closed, okay. The refrigerant, the hot liquid, will flow through expansion valve, and then it will flow through evaporator to complete the cycle, okay. So you can see that you don't have to do the repiping, so you don't have to take out some pipe and reconnect anything again. Everything stay the same. You can see that the piping, the set of equipment stay the same. You can just switch the reversing valve, okay. You can just switch the reversing valve, okay, this point, and it can make your system work as you would like in the winter time and in the summer time, okay. Same set of equipment, okay. So this is how it works, okay. The heat pump system that we normally use in the house to warm up our house, okay, in the cold climate country, when the winter is very cold and summer may be rather hot, okay. Alright then, I guess that concludes everything on the VCR and the heat pump lecture, okay. That should be the end of this lecture. See you next time in the last lecture of this course. That would be the liquefaction system. Goodbye.